The steelmaking process is the first stage in the manufacturing of steel coils and plays a crucial role in determining the quality and characteristics of the final product. Iron ore, which is primarily composed of iron oxide, serves as the main source of iron in the steelmaking process. It undergoes a series of steps to extract the iron and remove impurities. The iron ore is first crushed into small pieces and then washed to remove any dirt or contaminants. It is then further processed to concentrate the iron content, resulting in iron ore pellets or sinter. To initiate the reduction of iron ore to iron, it is necessary to introduce carbon into the process. Coke, a form of coal with a high carbon content, acts as both a fuel and a source of carbon. It is crushed and mixed with the iron ore pellets before being fed into the blast furnace. The intense heat in the blast furnace causes the coke to react with oxygen, resulting in the release of carbon monoxide gas. The carbon monoxide then reacts with the iron oxide in the iron ore, reducing it to metallic iron. Limestone is another essential component in the steelmaking process. It is added to the blast furnace as a flux, which helps remove impurities from the molten iron. When limestone is heated, it decomposes, releasing carbon dioxide gas. The carbon dioxide reacts with the impurities, such as silica and other non-metallic compounds, forming slag. The slag floats on top of the molten iron and is periodically tapped off from the furnace. The molten iron obtained from the blast furnace, along with the slag, is known as hot metal. It is then further processed in a basic oxygen furnace BOF or an electric arc furnace EAF to convert it into steel. In the BOF process, oxygen is blown into the hot metal, oxidizing impurities such as carbon, silicon, and manganese. The chemical reactions during the oxygen blowing remove these impurities, resulting in steel with the desired composition. In the EAF process, an electric arc is used to heat and melt scrap steel, which is then added to the hot metal to achieve the desired composition. The electric arc furnaces are commonly used for recycling scrap steel and producing specialty steels with specific properties. Once the molten iron is obtained from the steelmaking process, it undergoes further processing in a basic oxygen furnace BOF or an electric arc furnace EAF to convert it into steel. Both processes play a crucial role in refining the molten iron and achieving the desired composition for the production of high-quality steel coils. In the BOF process, the molten iron is transferred to a BOF vessel, which is a large pear-shaped container lined with refractory materials to withstand the high temperatures and chemical reactions. Oxygen is blown into the molten iron through a water-cooled lance. The oxygen reacts with the excess carbon and other impurities present in the molten iron, resulting in the formation of carbon monoxide gas. The oxygen blowing process in the BOF not only removes excess carbon, but also oxidizes other impurities such as silicon, manganese, and phosphorus. These impurities form oxides that react with the lime and other fluxes added to the furnace, forming slag. The slag floats on top of the molten metal and is periodically removed. In the EAF process, scrap steel is charged into the furnace. The electric arc is created by passing a high electric current between the electrodes and the scrap steel charge. During the melting process, the composition of the steel is carefully controlled. Alloying elements such as chromium, nickel, or manganese may be added to achieve the desired properties of the steel. Both the BOF and EAF processes are crucial in the production of steel coils. The BOF process is particularly suited for the production of large volumes of steel, while the EAF process is often used for recycling scrap steel and producing specialty steels. These processes allow for precise control over the composition and properties of the steel, ensuring that the final product meets the required specifications for various applications. Once the slabs have been prepared, they are sent to a stand finishing mill, commonly known as a hot strip mill. In this mill, the slabs are reheated to a specific temperature to make them more malleable. The reheated slabs are then passed through a series of rolling stands. These stands apply pressure and gradually reduce the thickness of the slabs, transforming them into thinner sheets known as hot-rolled coils. The rolling process also shapes the steel into the desired dimensions, achieving the required width, length, and thickness. The hot strip mill plays a crucial role in producing hot-rolled coils, which serve as a fundamental material for further processing and manufacturing applications. The hot-rolled coils produced in the hot strip mill undergo further processing in a tandem cold mill TCM to achieve the desired properties and dimensions. As the coils go through the TCM stands, they are subjected to both horizontal and vertical rolling forces. The combination of these forces, along with the controlled tension applied to the coils, allows for precise control over the thickness reduction and dimensional accuracy. In addition to reducing the thickness, the TCM imparts the desired surface finish to the steel coils. The rolls in the TCM stands have specific surface textures and profiles that transfer onto the steel during the cold rolling process. The cold rolling process in the TCM not only reduces the thickness of the steel coils, but also improves their mechanical properties. After passing through the TCM, the cold-rolled coils may undergo additional processing steps, such as annealing or coating, depending on the intended application. Annealing involves heating the coils to a specific temperature and then slowly cooling them to improve their formability and eliminate internal stresses. Coating processes may include applying protective layers, such as zinc or paint, to enhance corrosion resistance and provide aesthetic qualities. After the cold rolling process, the coils may undergo annealing to relieve internal stresses and improve the steel's mechanical properties. Annealing involves heating the coils to a specific temperature and then slowly cooling them. This process enhances the steel's ductility, toughness, and formability. A hot-dipped galvanizing line is an essential part of the steel manufacturing process, designed to provide a protective zinc coating to steel products. This coating enhances the corrosion resistance of the steel and extends its lifespan, making it suitable for various applications in construction, automotive, and manufacturing industries. The hot-dipped galvanizing line typically begins with the entry section, where steel coils or sheets are unwound and fed into the line. The steel passes through a series of pre-treatment stages to prepare the surface for galvanizing. These pre-treatment stages involve cleaning and chemical treatment to remove any contaminants, oils, or oxides that may hinder the adhesion of the zinc coating. The next step is the immersion section, where the clean steel is immersed in a bath of molten zinc. The zinc bath is maintained at a high temperature to keep the zinc in a liquid state. The steel is carefully passed through the bath using a series of entry and exit guides to ensure even and complete coverage of the zinc coating. As the steel enters the zinc bath, the molten zinc reacts with the iron in the steel surface to form a metallurgical bond. This bond creates a protective layer of zinc-iron alloy known as the galvanized coating on the steel. The thickness of the coating is determined by the speed at which the steel is pulled through the bath and the amount of zinc present in the bath. After immersion, excess zinc is removed from the steel by employing air, knives, or other mechanical means. This step helps achieve a uniform coating thickness and removes any excess zinc that may cause drips or unevenness on the galvanized surface. Following the removal of excess zinc, the steel is cooled in a quench tank or by air cooling. This rapid cooling solidifies the zinc coating, ensuring its adherence to the steel surface. Proper cooling is crucial to achieve a durable and uniform coating. Once the steel has been galvanized and cooled, it passes through a series of inspection and quality control processes. These processes involve visual inspection, thickness measurement, adhesion testing, and other quality checks to ensure that the galvanized coating meets the required specifications and industry standards. The manufacturing process at the aluminum complex starts with the extraction of bauxite, which is the primary ore for aluminum. Bauxite is mined from local sources or imported from other countries. Once the bauxite arrives at the complex, it undergoes a refining process to extract alumina, a white, powdery substance that serves as the precursor to aluminum. Next, The alumina is smelted in electrolytic cells to produce liquid aluminum. This process, known as the Hall-Héroult process, involves passing an electric current through a molten mixture of alumina and cryolite, a mineral that lowers the melting point of the mixture. The electric current causes the aluminum ions to migrate to the cathode, where they are reduced to molten aluminum. The molten aluminum is then cast into various shapes depending on the desired end product. It can be transformed into ingots, sheets, plates, or extruded into profiles. The aluminum complex utilizes advanced casting technologies and equipment to ensure high quality and precise products. To meet the increasing demand for aluminum, the complex incorporates recycling practices. Scrap aluminum is collected and processed to reclaim the metal, reducing the need for virgin aluminum production and minimizing environmental impact. The aluminum complex in Ras Al Khair also prioritizes sustainability and energy efficiency. It employs advanced technologies like cogeneration, which utilizes the waste heat generated during the smelting process to produce electricity.
The manufacturing process begins with the application of a release agent on the surface of the tilting table. A release agent is a substance applied to the mold or formwork to prevent the concrete from adhering to it. This step is crucial to ensure that the finished panels can be easily removed from the mold without damage. The release agent creates a barrier between the concrete and the mold, allowing for clean and smooth panel surfaces. Once the release agent has been applied and is ready, the next step involves positioning the separators on the table. Separators are devices or elements that are strategically placed on the table to define the shape and thickness of the precast panels. Proper placement of separators is essential to ensure that the panels meet the required specifications and dimensions. These separators act as molds or dividers that guide the concrete into the desired shape. After the separators have been placed on the table, it is essential to verify their final positions. This step involves meticulous inspection to confirm that the separators are correctly aligned and spaced according to the design requirements. Accurate positioning is critical because any deviations can result in panels that do not meet the specified dimensions, leading to production errors and rework. To facilitate the handling and transportation of the precast panels, nails are strategically placed within the concrete. These handling nails serve as attachment points for lifting equipment and are carefully positioned to ensure structural integrity. Proper placement of handling nails is vital to prevent damage to the panels during handling and installation at the construction site. Following the placement of handling nails, the manufacturing process proceeds with the vibration of the tilting table and screeding. Vibration is applied to the table to remove air voids and ensure that the concrete is uniformly distributed throughout the mold. This step helps in achieving the desired density and strength of the panels. Screeding, on the other hand, levels the surface of the concrete to achieve a smooth and even finish. Both vibration and screeding are critical for the overall quality of the precast panels. After vibration and screeding, it is advisable to cover the concrete with a protective material. This protective covering serves multiple purposes. Firstly, it helps in retaining moisture within the concrete, which is essential for proper curing and achieving the desired strength. Secondly, it protects the concrete from external factors such as temperature fluctuations and debris that could affect the quality of the panels. Properly covering the concrete ensures that it cures uniformly and reaches its full strength potential. Once the concrete has sufficiently cured, the next step involves the release and removal of the separators. Careful attention is required during this process to prevent any damage to the panels. The release agent applied earlier plays a crucial role here, allowing the panels to detach from the separators smoothly. Proper handling during this phase is essential to ensure that the precast panels maintain their structural integrity and dimensional accuracy. The manufacturing process of precast wall panels using a tilting table is a precise and efficient method employed in the construction industry. Precast wall panels are essential components used in the construction of residential, commercial, and industrial buildings. This process involves several crucial steps to ensure the production of high-quality panels that meet structural and aesthetic requirements. With the separators removed, the precast panels are ready to be lifted and removed from the tilting table. Handling equipment, such as cranes or hoists, is used to safely lift and transfer the panels to the designated area. The handling nails that were strategically placed earlier facilitate this process, ensuring that the panels are securely held during removal and transportation. The final stage of the manufacturing process involves the transfer of the precast panels to a storage area. This storage area is typically designed to accommodate the panels while they undergo further curing and quality checks. Proper storage conditions, including temperature and humidity control, are maintained to ensure that the panels continue to cure and develop their strength over time. The panels are organized and stacked in an orderly manner to prevent any damage during storage. Lastly, it is essential to emphasize the importance of regular and intensive cleaning in the manufacturing facility. Precast concrete production can generate dust and debris that can affect the quality of the panels and the efficiency of the equipment. Regular cleaning routines ensure that the production environment remains clean and free from contaminants that could compromise the final product.
The first step in the steel-making process is the collection of scrap metal. This includes a wide range of sources, such as end-of-life vehicles, demolished structures, and industrial waste. The scrapyard acts as a central hub where these materials are sorted and categorized based on their composition and quality. This sorting process is crucial as it determines the type of steel that can be produced from the scrap. Once the scrap metal is sorted, it undergoes a process called thickening. During thickening, large pieces of scrap are reduced in size to facilitate the subsequent melting process. This is achieved through the use of heavy machinery, such as shredders and shears, which break down the scrap into smaller, manageable pieces. Thickening not only improves the efficiency of the melting process, but also ensures a more uniform composition of the scrap, leading to consistent steel quality. This is accomplished through the addition of specific alloys and chemicals that react with the impurities, forming slag. The slag, which floats on top of the liquid steel, is then carefully skimmed off, carrying away impurities with it. The refining process continues until the desired level of clean. After refining, the liquid steel is ready for casting. Casting involves pouring the molten steel into specially designed molds called ingots or continuous casting machines, depending on the desired final product. In the case of ingots, the liquid steel is poured into individual molds, where it solidifies and takes the shape of the mold. These ingots can later be reheated and shaped into various forms, such as bars, plates, or beams, through subsequent rolling processes. On the other hand, continuous casting involves the use of a continuous casting machine, which allows for a continuous flow of liquid steel. The molten steel is poured into a water-cooled mold, where it solidifies and forms a continuous strand. The strand is then guided through a series of rollers that gradually shape it into the desired cross-section. Continuous casting offers advantages such as higher production rates, improved yield, and reduced energy consumption compared to ingot casting. After casting, the steel undergoes the final stage of production, which is rolling. Rolling is a process where the steel is passed through a series of rolling mills that progressively reduce its thickness and shape it into the final product. The rolling mills consist of sets of rotating rolls that apply pressure to the steel, causing it to elongate and change in shape. The specific arrangement and design of the rolls in each mill determine the final dimensions and properties of the rolled steel. The rolled steel may undergo further treatments, such as heat treatment, surface coating, or additional shaping, depending on its intended application. These treatments help enhance the steel's mechanical properties, improve its surface finish, or tailor it to specific customer requirements. A full scrap metal plant is a specialized industrial facility that processes and recycles various types of scrap metal. These plants play a crucial role in the recycling industry by recovering valuable metals from discarded or obsolete metal items and diverting them from landfills. The first component of a full scrap metal plant is the receiving area. This is the section where scrap metal is collected from various sources, such as individuals, businesses, construction sites, or demolition projects. The scrap metal can be in the form of cars, appliances, machinery, structural steel, copper wires, aluminum cans, etc. The receiving area is typically equipped with scales, cranes, and other equipment to weigh and transport the incoming scrap metal. Once the scrap metal arrives at the plant, it is sorted based on its type and composition. Ferrous metals containing iron are separated from non-ferrous metals such as aluminum, copper, brass, zinc, etc., using various techniques like magnets, eddy current separators, or manual sorting. The sorting and separation process is crucial for maximizing the value of the scrap metal and minimizing waste. The larger pieces of scrap metal are shredded or crushed into smaller fragments to increase their surface area. This process improves the efficiency of subsequent separation and sorting steps. The shredding and crushing step is typically done using specialized equipment such as shredders, crushers, or granulators. Magnetic separators are used to separate ferrous metals from the shredded or crushed material. Powerful magnets attract and extract ferrous materials, such as iron and steel, leaving non-ferrous metals behind. The separated ferrous metals can be sold directly to steel mills or further processed into different forms. Techniques like eddy current separators, air classifiers, or density-based separation methods are employed to separate different types of non-ferrous metals based on their properties. These processes help separate metals like aluminum, copper, brass, and others. The non-ferrous metal separation step is crucial for maximizing the value of the scrap metal and minimizing waste. Once the different metal fractions are separated, they are often melted down in high-temperature furnaces. This process allows for impurities like coatings, paints, or contaminants to be removed. Melting also helps recover valuable alloys and refine the metal to meet specific industry standards. The melted metal can be cast into different forms like ingots, bars, or billets, depending on their intended use. These newly formed metal products can be sold directly to manufacturers or further processed in downstream industries. Scrap metal plants usually have quality control measures in place to ensure the integrity of their products. Sample testing, chemical analysis, and physical inspections are performed to verify the metal's composition and quality. The quality control step is crucial for ensuring that the recycled metal meets the required specifications and standards. Scrap metal plants are often required to comply with environmental regulations to minimize the impact on air, water, and soil. They may implement pollution control measures, waste management systems, and employ recycling technologies to reduce emissions and minimize waste generation. The environmental consideration step is crucial for ensuring that the scrap metal plant operates in a sustainable and responsible manner. The processed scrap metal products are stored in designated areas until they are ready for shipment. They are typically organized based on type, size, and grade for efficient inventory management. The facility also handles logistics, arranging transportation for the metal products to buyers or downstream processing facilities. The material storage and logistics step is crucial for ensuring that the recycled metal products are delivered to customers in a timely and efficient manner. A full scrap metal plant is a complex and efficient facility that plays a vital role in the recycling industry. Through its various components and processes, it collects, sorts, separates, shreds, melts, and purifies scrap metal, ultimately transforming it into valuable and usable products. plant adheres to strict quality control measures and environmental regulations to ensure the integrity of its products while minimizing its impact on the environment.